Hey guys, today we're going to be presenting our Group 3 project. It's called ShortCut, and it has a goal of providing the shortest path between two cities and actually plotting that on a world map. So just a quick run through of the main function that powers this whole program is that we run our cities based on this structure called city node. And it just holds properties such as latitude, longitude, index, and city name. And it also has functions that get the distance between two cities, as well as the linear and rectangular coordinate system of it based on the latitude and longitude. And this uses the Mercator projection in specific. So we just read through our data set here. In this case, we're using a data set consisting of over 26,000 nodes. It also includes other fields. We filtered it to only read through the latitude and longitude and their names. And it passes that through the read data function.
Yeah, the read data function is basically just a simple parser where we take in all the three fields, we assign an arbitrary index, and we pass all of those into a constructor to create new city node pointers, and then we push them all back into a big vector that we then use for manipulation for our functions.
In this case, after we have all of the edges and the nodes into our vector, we don't have any inherent connection at the moment, so we have to generate edges. In the brute force scenario, we could create one edge to every other vertex, but that's going to be extremely expensive for other computations such as Dijkstra's. So what we do is we still do an O of n squared nested for loop operation, but we only create edges between cities with a distance of less than or equal to less than 100 miles. One thing that makes this actually optimized is that instead of doing this every time we start it up, we actually do this once. Then we can actually save those edges to a text file and then read them, turning it from an O of n squared startup to an O of e startup, which is actually much less. O of n squared is probably around over 670 million, whereas the number of edges we've determined is over only around 4 million. Now, we start the function, and we create the program, and it only takes a few seconds to load up and parse these data sets. Once this shows up, it's ready to go. We have a drop-down list of all the cities here, which is very extensive, so we can narrow it. So for example, let's choose a city such as Cairo and another far city such as Beijing. We have units from miles to kilometers, so let's try kilometers. We click calculate, only takes a few seconds, and we display the number of the distance in kilometers here. We pan around the map, zoom out a little bit more. We can see that there's a path here from Cairo to Beijing. It's curved as is the Earth. So that actually reflects the shortest path that we should take. And it actually lists the name of all the cities here in that order. As you can see, it goes all the way to Beijing right there. We can also try another one, and you can see how fast it updates because this algorithm is pretty fast with our optimizations. We've actually used a heap implementation of Dijkstra's, making it much more faster than the original. So we can do it from Cairo to Berlin, and it's already calculated up to then. One issue to point out with this graphing is not the calculation, but because we are using an image PNG and a linear calculation of coordinates using the Mercator projection, because the Earth is round, it's actually going to be less accurate as we go up north in terms of plotting it. Otherwise, the distances are correct. This, if you were to Google it, is very similar to the true distance. Let's try Tokyo to Hanoi in miles or kilometers. We can see here, it actually provides a realistic path. We do cross a little bit of a sea, but that is what we're looking for. In a local idea, we can go to miles, and we can do from Miami to Gainesville. As you can see here, it's only 322.9 miles. Now, we also have an option to compare it with the depth first search algorithm, which, as you can see here, takes a while to calculate, and it's very inefficient. The distance here is not optimal, and it takes a very big tour. Now, let's try something pretty weird. Let's go from Miami to Chihuahua, Mexico, and look at the depth first result. As you can see, it takes an extremely large tour around the entire continent before it reaches that, and that's because depth first search takes the first path it calculates and simply keeps going until it reaches its source. If we were to use Dijkstra's, and look at that distance, by the way, miles. Let's use kilometers, and actually let's stick with miles and look at the Dijkstra distance. It's very fast. And so that's our project, and thank you so much for watching.